Alright, what I want to do is go over a few of the problems with you from that sheet that we finished up on Friday, just to kind of point out a few things, or looking at a few people's answers. So there's probably some details that we need to go over because some people were making some common mistakes in there. First one I want to look at was number 7, and number 7, that's a speaker. It's just hanging by a cable here. And what we want to do is always try to identify the forces acting on it. This is 100 kilograms. Remember, the mass is not a force, but what that does allow us to do is that allows us to figure out what the force of gravity is. So we can always identify the force of gravity acting on the object, but the other force is from that cable, there's tension. So I have two forces here, and the fact that it's at rest tells me something. It tells me that the acceleration is 0. So when you look at the second law, you have this, F net equals ma. You're always looking at your free body diagram and the second law. And what we can do is we can take a look at, our forces. We always know how to calculate this. This would be m times g, which is a mass of 100 times 9.81. So basically, we know that this downward force is 981 newtons down. And now let's look at the net force. Because the acceleration 0, and even though the mass is 100, we get 100 times 0. That tells me that the net force is 0. Well, when we look at this, remember, this is the sum of all forces, and I only have 2 here. This quantity right here is telling me that all my forces need to add up to 0. So essentially what that means is that this force right here must also equal 981 newtons, however it's pointed in the opposite direction. Therefore, it'll cancel out. The other thing you can always do, and this is something that's a little more challenging to people, kind of just reason through this logically, but you can set this up as a math equation. Once you have the numerical value for F net, and you know that it's 0, what you can do is you can say, let me write another equal sign here and represent all my forces mathematically here. So what I could have done is I could put the tension and the force of gravity in here to represent my net force. And this is your opportunity to use mathematical sign to indicate direction. So my tension would have been positive and my gravity would have been negative. And then once we plug in the number for something we have, which was gravity, we knew that that was 981, and t is our unknown here. So if we move the 981 over to here, you get your tension value mathematically as well. So you can use math, you can use logic, you can use a combination of the two, and you can pretty much approach your problems that way. So that was an object that was at rest, that would remain at rest. If you looked at one of the other problems, it was also an object that was attached to a rope. However, that particular object, in number 10 I believe it was, there was a 5 kilogram bucket of water and it's attached to a rope, but this object is being accelerated upwards at 3 meters per second squared. So it's a little bit different. Now what is still the same is that there's tension acting up and there's gravity acting down. So if you look at these two diagrams, they look indistinguishable from each other right now. But this happens to be accelerating. So if we take a look at this object, it's obviously going to have a different force of gravity or weight here. It would be 5 times 9.81 mass times gravity. I get 49.05 newtons there. And now let's look at the net force acting on this object. Net force equals mass times acceleration. I know the mass is 5. I know the acceleration is 3. So that gives me a net force of positive 15, and it's always measured in newtons. Now, what that value literally tells me is that when I combine these two vectors, they should result in a net force of 15 newtons upwards. What that tells me is that this needs to be 15 newtons larger than this. Let's set it up mathematically just to see if that happens. So we know that the net force is 15. But let's represent our two forces here as the sum of tension and gravity. But remember, tension is up and gravity is down. And when I put in my number for gravity, 49.05. If I move it over to there, I would add 49.05 to both sides. So we would get 49.05 plus 15. And if you look at our tension value here, it is 64.05 newtons. So when I look at my tension, it is greater than the force of gravity. And when you look at how much greater this is than the force of gravity, it's 15 newtons greater. So when we say that there's a net force of 15 newtons, it's because this is 15 more newtons than this. Alright, I think there was one other problem that I wanted to look at. Let me scroll through the sheet really quickly, find it. It's actually back further, number 8. In number 8, it's a little bit of a different approach because you've got a skydiver and he's falling down. So here's our person. He's basically suspended in the air. We're told his mass is 75 kilograms. And there's a force of gravity acting on him. However, we were also told that there's a force of air resistance acting on him. So you have two forces acting on this person. And essentially, we're told what the force of air resistance is acting on the person. We said it's 100 newtons upwards. Well, at the same time, we can always calculate his force of gravity. We can calculate any object's force of gravity if we have their mass. So what we get is 75 times 9.81. I get that this is a downward force of 735.75 newtons. So when you look at these two forces, it's clear that the downward force is much greater than the upward force. So that means that this person will accelerate downwards. Now, we're basically, in the other problems that we looked at, not all the forces were known. Here the forces actually are known. And what we can do is we can work in the opposite direction. In the previous problems, we did F net equals ma to ultimately get to those unknown forces. Well, now we don't know the acceleration, but we can use our known forces to get to the acceleration. So essentially, when I'm looking at the net force here, I have 735.75 newtons downwards, 100 up. Now some of you might be able to go through this really quickly and just go, well, okay, I guess that results in 635.75 down after we basically remove 100 newtons from there because you got 100 newtons opposing it. Some people are more comfortable with the math here. So if I said F net equals ma, but once again, we try to represent the net force with our two forces here. Again, this is where I can use my signs. The air resistance is up, so I would make it positive, and the gravity is down, I would make it negative. My net force is comprised of these two forces. And we can put in the numerical values for everything. 75 is our mass here. The acceleration is unknown. The air resistance is 100. The downward force of gravity is not 6, 735.75. Now, when you do 100 minus 735.75, you get exactly what I said that net force was, 635.75. So if you're having trouble logically reasoning through it, setting up the math really will help you out here. And then all we have to do is divide both sides by 75. And what we're going to find is that we get the acceleration. And if we calculate the acceleration here, don't forget my negative sign that should be there. It is negative 8.4, I'll round it to 8 here, meters per second squared. And when we solve for that, we get the sign. That tells us that this person is accelerating downwards, which should make sense because they are falling down. And in addition to that, the last thing I'll point out is that if you look at this number, not quite as large as G. And that's because now we're looking at a little bit of air resistance here. So hopefully that conceptually makes sense to you as well.